Hi everyone, today I'd like to talk through some of the key ideas involved in the Sharpless Asymmetric Epoxidation. This is really one of the cornerstone reactions of asymmetric catalysis in organic chemistry. I'll lead you through the key ideas and end up showing how you can use the reaction to do kinetic resolutions and desymmetrization type reactions, and also why this reaction is particularly good at those types of things. If you enjoyed the video, please do give it a like and consider subscribing to my channel for more videos on mechanistic chemistry. So epoxides are very versatile functional groups in organic chemistry, can be used to make all sorts of complex molecules. If you just want to make any old epoxide, you would normally start with the alkene. I'm just going to start with cyclopentene here. And you'd react it with mCPBA, that's metachloroperbenzoic acid. That has this structure, and it's a cheap and readily available reagent. It's just a white powder that you can get out of your fridge and shovel into a reaction to turn your alkene into an epoxide. I should note that this only really works with nucleophilic alkenes. You can't get this reaction to work so easily with, say, alpha-beta unsaturated carbinols. So the key reactive part of this molecule is this weak OO sigma bond. And also we can note that this oxygen here is delocalized into the pi system with the carbonyl. So this bond is more electrophilic than a symmetrical peroxide, for example, because there's a delta plus on this oxygen here. I should also note that this whole bit over here with the aromatic conjugated system is just a leaving group. Okay, so if we want to maybe start setting some stereocenters on our epoxide, there are ways that we can do that using mCPBA. So for example, I'll just use my cyclopentene again, but I'll add a stereocenter with a hydroxyl group. So just to keep track, this is a chiral starting material. Now we'll notice the mCPBA reagent is able to use its perbenzoic acid moiety to hydrogen bond to that hydroxyl group. This allows us to sort of loosely tether the two molecules together. And so when our alkene attacks the mCPBA, if it's been dangled on the top face, it will preferentially react on the top face, and we will select for that as the product, in preference to the alkene just randomly attacking another mCPBA molecule on the bottom face. So I'm just going to extend my OH bond, and we can hydrogen bond onto our mCPBA reagent to show the reagent being held on the top face. So now when I do my curly arrows, the alkene can attack the weak OO bond. And normally we draw a mechanism like this. It's all concerted, all happens in one go to give us selectively the product where the epoxide is on the top face and also the hydroxyl is on the top face. So we select for the syn diastereomer. So this product will be formed in good DR, diastereomeric ratio. This is an example of a diastereoselective transformation. But because we're reliant on a hydrogen bond here, so an intermolecular force, we only really get good DR with this because it's not totally always stuck. We're just hoping for some intermolecular attractions. So chemists started thinking about how can we improve this? How can we get better diastereoselectivity? And one way we can think about doing this is to switch out that hydrogen bonding idea and change it into more covalent type bonding. So can we find a way of more tightly coordinating our oxygen source onto the molecule? And the next step was to think about using transition metals here. That's because we might be able to form some sort of complex. So you can have a think about your general transition metal chemistry, but we've got an awful lot of oxygens involved here. So we might want to think about oxyphilic transition metals for forming good complexes that can then pre-organize, deliver our epoxide to the face that the complex is tethered onto. So after some optimization, it was found that you could get a much improved DR. Specifically, it was found that you could use this vanadyl ACAC species in combination with tert-butyl hydrogen peroxide. That's quite a useful peroxide in organic chemistry because it's reasonably organic soluble. Things like hydrogen peroxide itself are just too water soluble, so often not compatible with your solvents for your reactions. So this complex could be represented something like this. So it's a reasonably covalent structure. You get very strong interactions with oxygens for sure. And it'll have two bidentate ligands on it. The ACAC ligand is just acetylacetonoate. And one way we could represent this could be like this. Other resonance structures are just as valid. So the main plan is to use this vanadium center to assemble oxygens around it so that they're all in close proximity and held there for a reaction to occur. So I can take my starting material alcohol and use the hydroxyl group as a new ligand for the vanadium. I can also bind on my peroxide as a ligand. And that vanadium is so oxyphilic, it will form quite a strong interaction with the vanadium itself as well. In doing so, that will make this position a bit more electron deficient. This is really good because it's essentially a Lewis acid activation of the peroxide in this complex. There's still likely to be one more thing on the vanadium, but it doesn't really matter what it is, so I'll just leave a squiggle there. So now we can see that the activated peroxide is held covalently on the top face of this molecule. So when the alkene reacts with it, so it can attack like this, the oxygen will get delivered to the top face, we'd normally finish these arrows off by breaking the weak oxygen-oxygen bond and forming the epoxide like this. We get much more preference for that syn diastereomer of product. Now, as always should be the question whenever you use a transition metal in a reaction, is it possible to make this catalytic in the metal? There are many advantages if we can do that. So the other question we want to address is how do we make this enantioselective? So that would be, for example, well, what if we didn't have a chiral starting material, maybe just some other allylic alcohol like this? We can actually exploit the idea that there's a remaining site here where we could attach another ligand on there. So lots of initial work on this area experimented with chiral ligands on the metal. The idea with adding chiral ligands would be rather than having the substrate dictate which face it would like the oxygen to be on, we can have a transition metal complex doing that instead. And some progress was made with hydroxamic acid ligands back in the 70s and 80s. But the real progress came when switching out the vanadium to another oxyphilic transition metal in titanium. And this is the basis of the Sharpless Asymmetric Epoxidation. So let's have a look at some of the reagents that were optimized for the Sharpless Asymmetric Epoxidation. That's the transformation of this allylic alcohol into the epoxide on the right in excellent enantioselectivity. So this reaction only works with allylic alcohols, as we need that hydroxyl group to bind to my transition metal in quite an efficient way. So the transition metal compound that we use for these reactions is titanium isopropoxide, and we need a chiral ligand. And one of the most versatile ones is diethyl tartrate. Now I need 1 enantiomer of that chiral ligand if I want to expect high enantioselectivity in my product. I'm just going to use the plus form in this example. So the advantage of these tartaric acid derivatives is that both of the enantiomers are readily available and super cheap. This particular enantiomer, well, the tartaric acid structure has 4 carbons and 2 alcohol groups in the middle. So there's an alcohol here, and we have one of the esters going down, so diethyl as the ester, and the other one goes up here. This is often abbreviated to DET. What we can see here is an option for a bidentate ligand using those 2 hydroxyl groups. And just as a reminder, what we're using that titanium for, well, this is essentially the scaffold. We're going to build our chiral ligand, our substrate, and our oxidizing agent all around some titanium centers. So we need our oxidant in there, and tert-butyl hydrogen peroxide comes to the rescue again with this. So that's the oxidant. You tend to do these reactions in dichloromethane at a low temperature, often around -20°C is quite common because we're trying to select a particular transition state. We're under kinetic control here. So the lower the temperature we can get away with, that's all good. Now, another practical consideration we need here is that you also need to add 4 angstrom molecular sieves. Now, these are a really good drying agent because if any water gets into this reaction, it will react really easily with a titanium isopropoxide, form titanium dioxide, precipitate out of your reaction really easily. That's a really stable compound. So it was found that the addition of these molecular sieves allowed you to use a catalytic amount of the titanium compound and a catalytic amount of the chiral ligand. That's the holy grail for these types of asymmetric catalytic processes in organic chemistry. Now, this is not the most straightforward catalytic structure ever, but I'm going to make an attempt at trying to draw what's going on. Titanium will often form octahedral complexes if the ligands are small enough to allow that. And that's indeed what happens in the proposed species that mediate this reaction. So it is thought that 2 of the titanium species come together with 2 of the diethyl tartrate ligands to form a very organized complex to start with. So how we might draw that? Well, there's a square of titanium and oxygen in the middle of this. So this is going to be an attempt at a 3D diagram. So a little square of your titaniums and your oxygens. Now these oxygens have come from the hydroxyl groups on the ligands. So there's a 5-membered ring. And again, on the left-hand side, another 5-membered ring. And this is quite a flat structure if we start thinking about the angles that might be involved. Now on the edges of this, we've got our ethyl group. So I'm just going to slot in my diethyl tartrate. It might be easier to have a look on the one on the right first because it's drawn in the same orientation as the one that I've drawn on the equation. Here we can see that the ester will be pointing down at this front carbon and there'll be a hydrogen pointing up, but on the back, the ester will be pointing up and the hydrogen will be pointing down. So to get the correct orientation on the other side, we just need to flip it round. So this time on this front carbon, the ester will be pointing up, and on the back carbon, it will be pointing down, the remaining positions still being hydrogens. So I've tried to emphasize the ligands on this diagram, but it's also thought that 2 of the esters on the bottom faces actually fulfill the vacant coordination sites that are going down on both of these titaniums. So actually there's an interaction here. Apologies for the slightly poor diagram, and another one over here. The remaining sites on the titanium are just filled with the isopropoxides that are left. So now both of those titanium centers are octahedral. So one of the cunning things that's going on here is that this is a C2 symmetric ligand, which means we can use either of the titanium centers here to bind the substrate and the oxidant and get the same result. So for clarity, I'm just going to take these isopropoxide ligands off at the back, just to give me a bit more space. And when this pre-coordinated complex finds the substrate and the oxidant, the internal link between that ester disappears at the bottom, and we lose two of the isopropoxides by binding the substrate and the reagent. Now, it's understood that the allylic alcohol, the oxygen of it, likes to bind in this position at the top here, indicated in red. There are two remaining positions on the titanium, going down and coming forwards at the front here. Just as before with the vanadium ACAT complex, the tert-butyl hydrogen peroxide likes to bind using both of its oxygens. That can add a bit of Lewis acid activation. The T-butyl group can keep itself out of the way because it's really bulky at the bottom. So that means it's this oxygen at the front, which is transferred to the alkene to form the epoxide. Now, just having a look at the rest of this transition state, we need to work out how the alkene can slot in. There's actually a little pocket for it to do so. This ester at the back, which is on the top face of the little table that we've made using the titanium and the oxygens, will act as a steric block and prevent anything pointing in that direction. We can see that this hydrogen at the front is not much of a steric problem at all. So we can put a bulky thing from the substrate pointing in that sort of direction. So just coming forwards in red, I can put the CH2, the methylene group, in here. And that allows me to come forwards and dump the alkene on top of the oxygen. And it works particularly well with transalkenes because this R group can point out of the way here at the front. So the reaction to form the epoxide will just be attacking the oxygen here. That will break this bond, and the remainder of the epoxide can be formed from this interaction. Now, we don't want to have to draw this out all the time whenever we're trying to predict how an alkene would react, but we can notice some other key features in here. Like, for example, this ester being in the way at the front on the left will mean it's quite tricky to put extra bulky stuff in this sort of space. So we might not see so great EEs if we're trying to use a substrate that puts something there. Additionally, just on the front, on the methylene group here, there are two more substituents. So there's potential for extra things to be in these positions too, not just hydrogens. It might not be so great for this one at the bottom to have such a bulky group there because that will be jamming straight into the template scaffold and mean that our substrate can't bind so easily. In fact, that would just mean if we were trying to assemble this reaction, the substrate wouldn't bind so easily, so reaction would just be slower if we can get it to happen at all. Now, to stop us having to worry about drawing all of this out every single time, there is a well-used mnemonic for this, a way of remembering how we get the reactivity, and it's normally something along this lines. So we try to represent that pocket as a parallelogram, where the alkene we're going to react sits in the middle in this sort of position. In this model, we always bind the alcohol from the substrate in this bottom right-hand corner, and our R group just goes up into this top bit. So sometimes you see people reminding ourselves that we don't really want to have too much bulk in these positions at the side, but we can tolerate a little bit. So how we reduce this model? Well, we start with our allylic alcohol at the top, and we swing it round and rotate it however to make it fit in this parallelogram. Here we can just slot it in quite quickly. Now, if we want the oxygen coming from the top face, so we want the oxygen to come down on this face here, we need to make sure we use the chiral ligand, which is the minus DET, so that specific enantiomer. As we can see from the diagram above, if we use the plus one, we get delivery from the bottom face of the alkene. So this is the one with plus DET. As a professional chemist, it's just worth knowing this mnemonic, however much of a pain it is. It's much less of a pain than the actual active catalyst. So this is a useful mnemonic. So that in total is pretty much the key points of how the mechanism works for the Sharpless asymmetric epoxidation. If you were in a lab doing this, this would probably be your starting point set of conditions. This is the classic setup. But if you were optimizing, say your EE isn't perfect or your yield isn't perfect, you still have lots of parameters that you can vary without having to use a whole new chemistry. So you can still vary the size of the ligand. So for example, you could make it a bit bulkier by swapping out those ethyl groups for isopropyl groups, which is usually abbreviated to DIPT, diisopropyl tartrate. You've still got the temperature that you can vary if needs be, but you still need it to be quite low. One final thing that you can do is vary the organic oxidant. A common thing that people can use in place of the tert-butyl hydrogen peroxide is cumene hydrogen peroxide, but there are loads of others in the literature you can have a look at. To go forwards with this, I just want to explain how we can use some of the kinetic factors to do some clever tricks with this epoxidation, particularly since we said the CH2 group at the front, well, potentially if there is a substituent on there, it might be jamming itself really badly into the catalyst structure. Alternatively, it might just be into empty space. So if you actually start off with a chiral allylic alcohol, by which I mean something like this, where rather than having just a terminal hydroxyl group, we turn that into a stereocenter. This actually allows us to do a cool trick, which is a kinetic resolution. Now, a kinetic resolution is when, well, say we had a racemic mixture of this, we can hope that one of the enantiomers reacts faster than the other. This will allow us to resolve our racemic mixture into two products, hopefully half of it reacting quickly and turning into an epoxide, and half of it with the opposite configuration staying as it is. Okay, the best way I can explain a kinetic resolution mode for this reaction is to use an example. So I'll take the substrate we had before. So that's the allylic alcohol with a methyl group on it. So this is a stereocenter, it's chiral. But what I'm going to do here is start with a racemic mixture. We could have made this by adding a Grignard reagent to an aldehyde, for example. So this is equivalent to a 50-50 mixture of the enantiomer where the hydroxyl group is coming forwards as drawn, and the one where the enantiomer has the hydroxyl group going back. If we had 100 grams of the starting material, we'd have 50 grams of each of these enantiomers mixed together. So the plan would be to put both of them into the Sharpless asymmetric epoxidation conditions and acknowledge that each of them will behave differently with the chiral active catalyst. This is exactly the same as if you're shaking hands with someone. Using your right hand, you can easily shake someone else's right hand, but it's much harder for you to shake their left hand. So I'll just give myself two parallelograms to work with. The alkene slots in the middle of both of these. The hydroxyl group always points into the bottom right corner. That leaves enough room for the R group up the top. And there's two more things we need to go for, which is what happens at this stereocenter here. There's a up position and a down position, and I'll just put that into both of these. In the top substrate, well, I need the hydroxyl group to be flat so it sits in the catalyst structure. That's actually going to force the methyl group to be up here and the hydrogen to be down. The exact reverse happens in the bottom structure where the hydrogen ends up at the top and the methyl group ends up down. Now to go forwards, we need to know which catalyst we've used. So I'm going to use, like we had before, the plus DET. Now plus DET prefers to add oxygens from the bottom face, and this is where we see the difference. On the top structure, there's a hydrogen pointing down, and on the bottom structure, well, we're going to have to go past the methyl group. Just sterically, that's harder. So the catalyst structure can't assemble itself so easily, which means that the reaction with this top enantiomer is actually very fast, whereas reaction for the bottom enantiomer is very slow. Now in this reaction, it turns out that there's a very big difference in rate, in the sense that all of the first enantiomer is likely to react before the second one even starts doing anything. And that means that you can end up with the top enantiomer, where the stereocenter is coming forwards on the hydroxyl group, will react with the oxidant and put on an epoxide on the bottom face, whereas the other enantiomer, where the hydroxyl group was pointing down, just sits there and doesn't do anything and stays as the alkene. Now, of course, if you leave this for infinite time, all of the possible alkenes will react and you lose all the benefits that you get. But say you left this for a few hours or maybe overnight, it's definitely possible to get these two structures in your flask. Then you can quench your reaction and separate these. You can just separate them by using normal column chromatography. The structure at the top is more polar, so it'll have a lower RF value in most normal phase systems. So the deal that we've brokered here is that we can get up to 50% yield, bearing in mind that only 50% of the starting material had this particular stereocenter at the hydroxyl group, but you'll get this substrate in excellent EE. Now you actually get a potentially useful byproduct here as well, is that you can get up to 50% yield of this enantio-enriched chiral alcohol. So this will also be an excellent EE. That might be useful to you anyway in your synthesis. Worst case scenario, if this is an undesirable byproduct, but your substrate is really important to you, you could always oxidize that up and reduce using sodium borohydride and do the same kinetic resolution again on that racemic product. So there's a related trick that we can play using this difference in reactivity rates, and that's to use this reaction in desymmetrization mode instead. Now, a desymmetrization is where we start off with a non-chiral starting material, we do an enantioselective transformation, and we end up with a product in high EE, and in this case, also in high DR. Again, best illustrated using an example. I'm just going to use this starting material, which is readily available. You can imagine adding 2 vinyl Grignards into an ester if you like to make that. But the key point is that it's not got a stereo center in the middle. Two of the groups are the same. So this is achiral, but it's also got two alkenes that could react, both of which are in the allylic position. So they're perfect for the Sharpless asymmetric epoxidation. Okay, so let's see what happens. Let's put it into the Sharpless asymmetric epoxidation reaction conditions. I'm going to need the parallelogram again to explain what's going on. Alkene in the middle, hydroxyl group coming towards the bottom left, but this time there's no R group. But we still have the substituents at the front, purple one going up and one going down. We need to know which catalyst structure we're going to use. So I'm just going to use the same one again. So using plus DET. Now this means we deliver the oxygen from the bottom face. But differently this time, we actually have a choice. We can rotate that molecule however we like to put the remaining hydrogen into either of those positions. So I'll just draw another parallelogram just to keep track of absolutely everything here. So the hydrogen could slot itself on this top structure at the bottom and the remaining vinyl group into the top position, or the vinyl group could go on the bottom face and put the hydrogen on the top face. So we can now see that if we want to deliver oxygen from the bottom, it would be much faster on this top substrate that's only got the small hydrogen versus the vinyl group on the bottom structure. So that means that this is fast and the one at the bottom is slow. So if you've got the conditions just perfect for your substrate, all is really good. You make the epoxide on just one of the alkenes, so that's coming from below, and you get a stereo center on the hydroxyl group as a bonus. So here we get excellent EE and DR. And what's more, if that top reaction is really loads faster than the bottom reaction, you can get up to 100% yield of this, no problems. Now, unfortunately, the world isn't perfect, and that might not be the scenario you end up with. But this asymmetric epoxidation has another cunning feature that helps you out. Just looking at what the product would be for the one down below, we'd still get the oxygen delivered to the bottom face, but this time the hydroxyl group will be going backwards, and that would be our remaining alkene. So what we'd expect here is still to have really good EE and DR, but it's for a different diastereomer. So the relationship between these two are diastereomers. Now that can be useful because it could mean that you could separate these on a column, but they're very similar in structure. And trust me, when you've tried to do this, they end up being spots very, very close to each other. So that's often a very tricky task. But there's actually a cunning extra feature to this reaction that means we often don't need to deal with this problem. And that's the fact that both of these are still allylic alcohols. So in principle, they're substrates for a further asymmetric epoxidation. So putting the remaining alkenes into these parallelograms and the hydroxyl group, we've got the same situation as before, where there's two positions that we need to account for, and we're delivering oxygen from the bottom face. Now you need to rotate things around in your head a little bit here, but you should end up with this one being the hydrogen at the top and the epoxide at the bottom. And the reverse will happen in the bottom structure where the epoxide ends up at the top and the hydrogen at the bottom. Now this is really good because that means that this top substrate is very slow at doing a further reaction. But this one at the bottom that we probably didn't want anyway is actually very fast. So if you like, we're destroying this extra diastereomer that we didn't want by letting it react further. This is actually a good argument for adding just a little bit more than one equivalent of your oxidant in these reactions to allow this effect to help you. So this one will form the bis epoxide with this stereochemistry, and this one is more easy to separate. So with all of these factors working together, we've got a really good way of making this substrate in the middle for further synthesis in high EE and high DR and high yield. If you enjoyed this discussion, please do give the video a like and consider having a look at some of my other videos on organic chemistry mechanisms and subscribing to my channel if you want to know when future ones drop.